Welcome, everyone, and thank you for joining our discussion today. This is Mike Furstenberg, and I'll serve as your moderator for this webinar. In keeping with standard practice, all participant lines are muted. Please enter any questions you may have in the question box at any time. We will address all submitted questions at the end of the presentation. All webinar registrants will receive a follow-up email, including information on how to access a recorded version of this webinar, along with registration information for upcoming webinars on similar topics. Today's topic is, what do really secure OT ICS sites do differently? Presented by Andrew Ginter. Andrew Ginter is the VP of Industrial Security at Waterfall Security Solutions and works with many of the most secure industrial sites on the planet. He is the co-chair of ISA's SP99 Working Group 1, a co-author of the Industrial Internet Consortium Security Framework, and the author of 2 books on industrial security, SCADA Security, What's Broken and How to Fix It, and Secure Operations Technology. Andrew spent 20 years developing SCADA system and IT/OT middleware products, and another 20 designing control system security products. He holds a BS in Applied Mathematics and an MS in Computer Science, both from the University of Calgary. Andrew?
Thank you, Mike. And thank you, everyone, for joining us and for listening in. As Mike said, I'm talking today about secure operations technology. This is my latest book. As Mike said, the book is about what the world's most secure sites actually do. Now, I work for Waterfall, but the book is not about Waterfall. Many of the world's most secure sites, Waterfall serves that market, but the book is not about us. It's about what we see these sites doing. And I submit that, these sites are our future. The threat environment continues to get worse. What these sites are doing today is what all of us need to be thinking about doing tomorrow. These sites, the book is really about what these sites do in addition to what everybody else does, what they do differently from what everybody else does. These sites do a lot of what everybody else does. That's not what the focus of the book is. The focus is what they do differently, how these sites see the world differently. They ask different questions. They get different answers. They see security differently. And as I said, even though the book is not about Waterfall, it's about security. It's about the world's most secure sites and their perspective on security. Waterfall has purchased a batch of the books and is making them available free of charge as a public service. We're able to ship to, I think, most of Europe. And so if there will be a URL on the end of the presentation. If you would like your own copy of the book free of charge, drop us a request and we will get a copy off to you so that you have it as a ready reference. So let's begin. Let's talk about conventional security. And this is the kind of stuff that we see a lot of sites doing. This is the conventional approach to security really was captured in the first generation of industrial security standards, vintage about 2007 through 2012. What is conventional security? It's intrusion detection and security monitoring and incident response. It's the NIST framework. It's identify, protect, detect, respond, and recover. There's passwords and permissions. There's antivirus systems everywhere we can put them. There's security updates everywhere we can put them. There's host hardening everywhere we can do it. And a lot of the time, a lot of this stuff is really hard to do on industrial networks. Security updates are very expensive because every change to the system risks a malfunction. you know, the whole point of security at industrial sites is to prevent, you know, unexpected shutdowns and worse. Yet, if we have a blue screen from a security update that, you know, didn't work, that was incompatible, if the security update causes our control system to malfunction, bang, right there we have the unplanned shutdown that we were trying to avoid. You know, the cure is worse than the disease with some of this stuff. So, you know, when I say antivirus wherever we can, encryption wherever we can, it's, you know, it's difficult to do some of this stuff. And the vintage, you know, 2007 through 2012, 2013 advice basically said, yeah, it's hard to do some of this stuff. Do it anyway. Invent a way to do it. Find a way to do it, because this is the only way we know how to do it. You know, back then, really, there was not a strong, you know, industrial security practice. We had to rely on enterprise and IT security practice, and this approach really reflects the enterprise and IT practice applied to industrial systems. So, you know, we have lots of security because we have lots of attack vectors. We have laptops that can be carried in. We have USBs that contractors and employees are dragging around with them. You know, attacks can come in online. They can come in remotely. They can come in with stolen passwords, with guest passwords, with SQL injection attacks. You know, so we have to deploy a lot of security. You know, the bad guys only need to find one way, and it's not easy being the good guys. We have to defend against everything coming in. And when we've deployed all of that stuff, what are we left with? Well, you know, there's still a residual risk. The first law of cybersecurity, nothing is secure. There's always a way in. There's always something the bad guys can still do to us. And so the whole question transfers into a question of risk management. You know, what's classic risk management? In classic risk management, there's only three things you can do with risk. You can mitigate the risk, which is do something to reduce the risk, reduce the possibility of attack, reduce the consequences of attack, reduce the frequency of attack, but do something to reduce the risk. You can transfer the risk, usually by buying insurance. You pay someone else to take the risk. If the risk is realized, if the incident occurs, the insurer reimburses you. It's the insurer who's at risk, not so much yourself. And we can accept the risk. Any risk we do not do anything about, any risk we do not mitigate or transfer, by default, we accept. It means we're stuck with it. It means if the risk is realized, if the consequence occurs, it's on us. We pay for it. So, the residual risks are what's left over. What are those risks? Well, you know, if the bad guys get into our IT network, well, we act. You know, in the NIST framework, in that terminology, we detect, we respond, we recover. Respond and recover means identify the affected machines. It means isolate them. It means erase them, restore them from backup, and repeat. This is what we do on enterprise networks. The problem with these residual risks in the industrial space is this: if a refinery or a plant goes down, you know, because of a cyber attack, we can't restore lost production. We can't restore damaged physical equipment. We can't restore human lives and human casualties. We cannot restore them from backups. So the question is, you know, are these residual risks on industrial networks, are they really acceptable? You know, some people will say, well, of course they're acceptable. We accept them, don't we? Therefore, by definition, they must be acceptable. This is not what we see the most secure sites saying. They consider the residual risks from many of these conventional cybersecurity programs to be unacceptable risks. And so they raise the bar. Which brings us to Psychot. You know, the number one priority of conventional enterprise security programs and even industrial security programs is to protect the information. You know, I was on security. I was one of the instructors on security training over the last week, remote training over to India. And heard time and again, one speaker after another get up and say the number one priority on enterprise networks is protect the information, protect the confidentiality, the integrity, the availability of information. And every one of them said, but on industrial networks, the priority is reversed. They all said, on industrial networks, you protect availability first, or some of them said you protect the integrity first. What we see the world's most secure sites doing is not protecting the information. That's not their number one priority. I mean, the number one priority at every physical site I've ever had the privilege of visiting, and bluntly, I don't get out much, but the few sites I've been able to visit, I had to write a test to make sure I understood the safety procedures before they let me set foot on these sites. The number one priority at the industrial sites I've visited is safety. Don't kill anyone, don't cause a public safety catastrophe, don't damage the environment. The goal at the, more generally, the goal at the secure industrial sites that I work with every day, their number one security goal is not to protect the information. It is to protect physical operations, protect continuous, correct, and efficient physical operations. Protect physical operations from information, because all information can carry attack. We need to protect physical operations from attacks that may be embedded in information. So the secure sites really do see the world differently. They don't talk about protecting the information. They don't talk about CIA or AIC or IAC. They talk about physically protecting, the physical operation. Now, don't get me wrong. These sites do all of that protect the information stuff too. It's just nowhere near their first priority. They do all of that. You have to protect the information. You have to do all of that conventional security stuff. But what these sites do is they do more on top of that. And because they've done more, because they've done some very powerful stuff that I'm going to go through here, they might relax just a little bit the most expensive and the least effective security measures from the conventional space. They might, apply security updates at longer intervals. They might, but they might not deploy antivirus everywhere. They pick and choose because the extra measures they've taken have given them options to reduce the cost of the most expensive and the least useful parts of the conventional security paradigm. But they can only do that because they've deployed these other very strong measures that I'm going to be talking about. So they do the conventional stuff. For them, the conventional stuff is just not enough, though. So, I mentioned the first three laws of SCADA security. The Psychot perspective is rooted in this perspective that I documented in my first book. Let's go through these real quick and start bottom up, because that's sort of the way that the Psychot folks think about them. I got the order wrong, in my red book. But number three, all cyber attacks are information. This is what cyber means. It's the definition of cyber. All cyber attacks are information, and every bit of information can be an attack. I mean, a single bit can be an attack. The bit might say, open the valve. And that message with that bit might be exactly the right thing to do right now. But 10 seconds from now, that bit might have to be a 0. It might be time to close the valve. And if we send that bit as a 1 again, change that 1 bit, that's an attack. Okay, somebody has told the physical process to do the wrong thing. Number two, all software can be hacked. I wrote software for 20 years, and in spite of my best efforts, in spite of the best efforts of the teams that I was on, the teams that I led, not one piece of software that we produced was ever free of bugs. All software has bugs. Some bugs are security holes. Some of these security holes have, we've discovered, and we have fixes available, or we're in the process of fixing. Some of these holes we have not discovered, but our enemies may have. In practice, all software can be hacked. All software has bugs. And number one, nothing is secure. This is what I was getting at with the risk assessment slide. Intrinsically, there's always a way to get in. The question, the security is not a binary state. It's not, yes, I'm secure, no, I'm not. Anyone who uses words like secure communication or secure boot or secure trusted platform module or secure root of trust, anyone who uses secure as an adjective is selling something. Okay, they're trying to get you to buy something. Nothing is secure. We can talk about communication security. We can talk about, clean boot security, but nothing is secure. There's always a way in. Enough time, money, and talent, there's always a way in. The question, are we secure, is meaningless. The question, how secure are we, has an answer. The question, how secure should we be, is even more important. And these are the questions we hear in the world's most secure industrial sites asking. And the other thing they do is, I see in a lot of risk assessments, I do a lot of risk assessment work with these industrial sites. In a lot of these sites, compared to sort of conventional sites, the difference I see is that the truly secure sites are really paranoid. They assume that, if every CPU in their system is compromised, they assume that every one of those CPUs is going to issue every unsafe instruction that it's physically able to issue to the industrial process. They look at worst case scenarios. What I see with a lot of sort of conventional sites doing is focusing on high frequency, low impact attacks. And this is a problem. We need to consider, we do need to consider high frequency attacks. We also need to consider low frequency, high impact attacks, attacks that will put us out of business. So, how do we raise the bar? How high can we raise the bar? Let's start with security law number 3. All cyber attacks are information. Fundamentally, the only way an industrial control system can change from an uncompromised state to a compromised state is if information, attack information, enters the control system across a physical perimeter or a network perimeter. All cyber attacks are information. There's no other way for attacks to compromise a site. The IT gurus, they tell us the perimeter is dead. Where's the perimeter around our cell phone? How much vital data is on the cell phone? Well, they're right. The perimeter is dead on enterprise networks. But every important industrial site I have ever visited has both a physical and a cyber perimeter, has a fence, has guards, gates, and guns. And you ask me, well, what's an important site? Don't ask me. The physical security people have been figuring this out for centuries. They know when you need to build a fence around a site to protect the public from the site, to protect the site from the public. What I observe in these secure sites, though, is that if there's a fence around it, if there's a physical perimeter, there's also an equally strong cyber perimeter. So, secure sites define the physical and cyber perimeters of their control critical networks. They define a control critical network and they draw a line around it. They take an inventory of all of the ways that information can enter that critical network through physical or cyber perimeters. A complete inventory of information flows is also a complete inventory of attack vectors. So now they have a complete inventory of all possible attack vectors. And what they do is they set out to systematically control those attack vectors. They prefer physical control over those information flows rather than cyber control. They set out to systematically, physically control all of the attack vectors because, why don't they use software? Because, all software can be hacked. Using vulnerable security software to protect our vulnerable control system software just doesn't make any sense to these sites. They do it, but not as their primary line of defense. They do deploy software security as secondary defenses. So once we have our inventory of attack vectors, what do we do with it? Well, we need to set about systematically controlling those information flows. How do we do that? There's only two ways There's only two ways that information can move. It can move online and offline. You know, online is you know, through wires, through fibers, through the air with wireless communications. With online communications, there's no visible movement of physical matter as, you know, moving the information. With offline information flows, there's always something physically moving. A cell phone is carried from A to B. A USB drive is carried from A to B. My head is carried, you know, on my neck from A to B. I can, you know, I personally can carry out an offline attack if I cross a physical security perimeter with a password in my head and malicious intent. That's attack information I'm carrying into the site in my brain. So chapter 4 in the book is all about protection from offline information attack flows. You know, the most common of these, the single most frequent mechanism for carrying attacks is removable media. So wherever practical, you know, these sites, they glue shut all of the ports. They remove the CD drives, they remove the floppy drives from the older equipment. They glue shut the USB ports. They physically block as much as possible all of the ways to carry media into the site. And, you know, when you have to carry media in, and you do sometimes, they use a kiosk at the physical boundary, an antivirus scanning kiosk. You know, something like Honeywell's Secure Media Exchange or the OpSWAT kiosks. These are mechanisms where you bring your media in. It might be a CD, it might be a USB drive. You pop it into the kiosk. It scans it with, you know, typically between 4 and 12 antivirus engines, and the 3 files that you need, you copy to brand new media. You leave your media behind. It may be contaminated. You write the clean files to clean media. You pick up the bright red, the control system labeled media, and you use it. And what do? You physically take it to another computer right beside the kiosk. You plug it in. You load the files onto the industrial network, and you leave the media behind. Now the files are on the network. They can move around the network, you know, as they need to. You know, so again, this is something that, you know, removable media controls is something that everybody knows about. But, you know, what these folks do is they sort of take it to another level. It's not scan the media with an antivirus. It's scan it with 5 or 8 antiviruses. It's not once it's scanned, you can use the media. No, they leave the media behind. They copy it to clean media. And this really is an example of what they do for simple files, files whose content we're fairly confident of. Complex files, not so much. They don't go straight into the control systems. You know, what's a complex file? A software update. It's full of code, tens of megabytes of new code. Is any of that code an attack? Well, how are we going to tell? This stuff does not go directly into the control system. It goes into a test bed. The test bed is instrumented. It's, you know, the test bed's designed in the old days to test for threats to reliable operation, threats to safe operation, threats to continuous operation. But in the sites I work with, the test bed is also instrumented for security. It's like a sandbox. You can advance all the clocks on the test bed, and oh look, all the hard drives were just erased. Good thing we didn't take this into our control system. That's the purpose of the test bed, is to discover nasties like that. So on the test bed, we turn on all the auditing, all the logging levels, we investigate all the false positives so that we can gain information in new complex artifacts of information. And, you know, one example of sort of the most secure approach to offline security is a near-miss protocol. You know, a lot of these measures, you know, on the previous slide, a lot of these measures are going to seem fairly familiar. We've all heard about removable devices, you know, laptops being carried around. We've all heard about supply chain problems with new computers coming in. You know, most of our security programs are doing something about this. But what's different with the world's most secure sites is not the kind of thing they're doing with offline protection. It's the intensity that they bring to it. So for example, something we're seeing at some of the leaders in the space is what's called a near-miss protocol. We're all familiar with the OSHA safety near-miss protocol. So if I walk through a plant, with my hard hat on and my steel-toed boots, and I walk under a 10-ton load that a crane has in the air, and 5 seconds after I pass that, the chain snaps and the load drops to the ground, big thud behind me. Well, I wasn't injured. It's not a safety incident. It is a near miss. If circumstances had been just a little different, if I'd stopped and looked down for 5 seconds, I'd be dead. I'd have 10 tons on top of me. So, what happens with near misses in the safety world, you write them up, you submit them. A committee on the end of the month looks at all of the reports and tries to draw conclusions. With statistics, if there's enough of them, but looks at them and says, what can we do to improve safety in a cost-effective way? And they're doing the same kind of thing for cyber events. If I walk up to an industrial control system machine and pop my USB in, unplug the keyboard and pop my USB drive in because it's a USB keyboard and I've got stuff on the drive and I haven't followed procedure here, there's going to be an alarm go off. So it's not just physical protection. Again, these sites have software protection as well. You put the USB in, an alarm goes off. I get a phone call from the safety officer, from the security operations center saying, hey, you're not supposed to do that. And every one of those alarms that the SOC gets for the control system is written up as a security near miss. These things are aggregated, they're summarized at the end of the month, and we conclude that, 1/3 of the near misses this month were from Andrew. Somebody give that man a renewal on the security training, would you? This is how to make the site more secure. These sites report that with the combination of removable media controls and the near miss protocol, they essentially eliminate errors and omissions with USB drives, with removable laptops, with other devices. Now, when it comes to online controls, the Psychot protections differ sharply from IT security protections. The big difference that everybody notices right off the bat is that Psychot sites forbid firewalls between control critical networks and the industrial networks, between their control critical industrial networks and any external networks, and usually enterprise networks, but they forbid firewalls between protected networks and networks that are not managed according to the Psychot protocol. They permit only unidirectional gateway technology at those connections. This is not something that Waterfall invented, even though we are a vendor in this space. This is something we observe in these sites. They forbid firewalls between their protected networks and their unprotected. Now, don't get me wrong, they still use firewalls extensively inside their critical networks. They still use firewalls extensively outside the critical networks. They generally deploy only one layer of unidirectional gateways right at the boundary, between the two networks. They deploy one layer of gateways. They only replace one layer of firewalls in a defense in-depth Purdue style stack. Now, to anyone not familiar with the gateways, here's a quick look inside. Unidirectional gateway hardware. Basically, everything in the red here is a gateway. The hardware in the center and 2 CPUs. Now, the most popular packaging for gateways that we observe in the marketplace is a 1U rack mount unit that has everything in the red in the unit. I've called it out to 3 pieces to highlight the fact that there's 2 pieces of software involved, and there's the special hardware in the gateway. So unidirectional gateway, the hardware is physically able to send information in only one direction. There's a fiber optic laser on one circuit board, there's a receiver on the other board, there's a short piece of fiber in between. We can send from one circuit board to the other, but there is no laser on the receiving circuit board. It's not physically possible to send any photons back. We can physically only send in one direction. What does this mean? Well, it means that even if an attacker has figured out a 0-day vulnerability in every piece of software on the planet, every piece of security software on the planet, even if they've stolen every password for every account on every computer on the planet, it's not physically possible to send any information back from the enterprise network or from the internet back into the protected network. If there's no way to send the information, there's no way to send the attack. It does not matter how sophisticated our enemies are. You know, the hardware is only one way. And there's software that's part of every gateway as well. The software makes copies of databases and emulates devices. So, you know, when there's a historian on the inside, Unidirectional Gateway software asks the historian, normally, username and password, asks for all the data, converts the data into the weird one-way formats, and sends it through the weird one-way hardware, and the software on the other side logs into an identical database. You know, if it's SQL on the inside, it's SQL on the outside. If it's Pi on the inside, it's Pi on the outside. Logs into another database and inserts the data into the database. And now we've got a copy, a replica on the outside network, a copy of the inside network. Anybody on the outside who wants the data asks the replica for the data and gets the same answer as the industrial database would have provided, because all the data is there in the copy. So again, that's the idea: one-way hardware and software that replicates servers. But you know, a lot of people, the standard learning curve with this technology is that can't possibly work. And then you look at the server replication and go, I guess it could work. But look at my network. It can't possibly work for me, because like I said, most networks are very confusing. The average site doesn't have one network. The average industrial site has dozens of networks. There are, you know, different networks for different parts of the plant. There are different networks for the PLCs versus the HMIs versus the historian DMZs. And all these networks have to talk to each other. If each of them can send and nobody can receive, it just doesn't work. So what do we do about this? What we need to remember is that there's only one control critical network at most of these industrial sites. Most of these sites they define their control critical network to contain most or all of their other industrial networks. So, you know, the Psychot sites that I've documented, they forbid firewalls at connections between the two classes of networks. That's where they demand a unidirectional gateway. But what we see is that inside the control critical network, there's a lot of firewalls. Outside the control critical network, there's a lot of firewalls. You know, firewalls are used between networks that are managed as being at the same level of criticality. We demand a unidirectional gateway only for connections between networks at different levels of criticality, at the critical network boundary. So a lot of people look at this and they say, you know, is that even practical? You know, is that even going to work? Look at the industrial Internet of Things, the IIoT. The trend for 30 years is more and more communications, more and more connectedness. The industrial internet is held up as the future of industrial control systems. But, you know, let's look at how this really works. I mean, I'm a co-author of the Industrial Internet Consortium Security Framework document. You know, a Waterfall person is the chairman of that committee. You know, we're very connected with the future of industrial security. The framework is based on the IIC, the Industrial Internet Consortium reference architecture. This is an architecture that was developed by and agreed to by a consortium of over 300 vendors. You know, this is the consortium's reference architecture diagram, cut and pasted. It's their colors. You know, I didn't make this up. The industrial control networks are at the bottom, and information flows are the arrows. Within the control network at the bottom, information circulates reasonably freely. You know, think firewalls inside the networks at the bottom. But at the higher levels, there are white and green and red arrows. You know, my apologies to the red-green colorblind in the audience. This is the IIC's colors. The white and green arrows are safe communications. They're the arrows from lower levels to higher levels in the architecture. They're the arrows between components at the same level of the architecture. The downward arrows are all red. Why is that? It's because the downward arrows all represent some kind of control. Each and every message that's sent into a lower level of the architecture makes the computers in that layer of the architecture, makes those computers execute instructions they would not otherwise have executed. And so every message downward is a kind of control. It's a potential attack. And so, of course, the most dangerous control messages are the ones entering the control critical network at the very bottom here. You know, entering that network from higher layers. What do we do about those messages? Well, you know, if all we have is a firewall, well, what do? What can you do with a firewall? You open another port. You know, to a man with a hammer, all the world's a nail. To a man with a firewall, all problems are solved by whack, open another TCP port. Modern practice, though, you know, demands, this is what's documented in the ISE framework, by the way, demands disciplined control. When we have no choice but to send control information into a more critical network, and we do need this, you know, we need to use the most secure, the most specific, the safest way that meets the industrial need. And you know, as a reminder, all of the offline information flow mechanisms I mentioned a couple of slides ago, those are all kinds of control as well. The OT test bed is a very kind of discipline for those control information flows. It's an offline discipline. It's a very slow discipline, but it's as safe as we know how to make it. So, you know, we're talking about online discipline, you know, information flows. How can we discipline online flows? Here's a classic design. A control network has a lot of equipment in it. You know, includes an OPC server. A historian sits in a DMZ between the control network and the IT network. A business system in the IT network needs data from the historian, you know, to do billing, to optimize operations. This is a classic design. The business system sends queries to the historian and gets answers back. The historian sends queries to the OPC server and gets answers back. You know, between each of these networks, there's questions and answers, there's queries and responses, you know, intrinsically two-way communications. And, you know, if these queries are polite, well, then we get data back. If they're nasty, well, we're attacking the more critical networks right through any firewall that we might have put between these networks. So here's one thing we can do. We can deploy unidirectional gateway technology at the boundary between the control network and the DMZ. And this is, you know, this kind of thing is documented by the industrial internet. You know, this is the modern approach to dealing with control. Put a unidirectional gateway in between these layers, and the gateway can poll the industrial OPC server. It can grab snapshots of the current state, all the tags, all the values. It can convert the snapshot to the weird one-way formats, push that snapshot out, and on the outside, there's, again, remember, inside the gateway, there's two CPUs. There's a CPU on the outside. The CPU on the outside can be a standard OPC server. So the gateway has an OPC server in it. It has all the latest data. Now, when the historian, you know, so this dashed line here, that's the replica OPC server. That's the gateway's OPC server, a virtual OPC server, if you like. The historian can ask the gateway's standard OPC server for data and get the same answer from that server as would have come from the real OPC server, because the gateway's OPC server has a complete snapshot of the state of the real OPC server. We did not open a port and let requests through. I mean, with OPC, you'd have to open thousands of ports to let these requests through. It's nasty, it's decom. We did not open a port. We eliminated the need to send any requests at all from the outside world into the industrial network. Getting rid of inbound information flows entirely is the best way to discipline attack information flows. Really, what we did was we defined the control system network as our control critical network. We defined everything else as non-critical, and we deployed one layer of unidirectional gateway technology as the only connection between the control critical network and the non-critical network. Now, you know, I'm guessing a lot of us have heard of this unidirectional stuff before. You know, we may not really have looked into it. You know, we may have looked into it little and concluded it can't possibly work for us. What's new in the Black Book is a catalog of 20 different unidirectional network architectures. 20 architectures documenting how different kinds of sites with different kinds of communications needs and different kinds of networks use the unidirectional gateway technology. So the OPC example we just went through, that's number 2. It's an example of device emulation. We're emulating the OPC server. In a couple of years, this is the part of the book that's most likely to need an update. We continue to see new architectures coming out of the experience of pioneering sites in this space. And a lot of these network designs are a little bit counterintuitive. So, let me go through another one here. I'm thinking a lot of us might be thinking I cheated on the OPC example. I mean, eliminating inbound information flows entirely is certainly discipline, but it's not particularly control. So let's take an example of a network architecture where we need, or at least we want, online inbound communications. Some industrial sites want to push antivirus signatures into their systems automatically on a regular basis. Batch systems need to top up their inventory of production orders a couple of times a day as well. That stuff has to come into the system automatically as well. These are comparatively small documents, comparatively infrequently. How do we deal with these automatic incoming flows of information? Well, again, what we see secure sites doing is deploying unidirectional gateway technology. But in this case, they've deployed a reversible gateway. Waterfall calls this the flip. The gateway replicates, OPC servers and historians and whatnot out to IT network all day long, but a couple of times a day, it reverses orientation. This is a reversible gateway, not a normal gateway. It's still a kind of unidirectional gateway. The flip really can only send information in only one direction. It has only one transmit circuit board. It has only one receive circuit board. The device, has a button in front or has a timer inside, and you can use it to reverse orientation. So, 2 in the morning, typically 2 in the afternoon, typically for 10 minutes, the device, it's as if it picks up, flips over, and sets down. It can be one way out or one way in, but never both. And while it's oriented inwards, it does not forward traffic. It does not forward network traffic like a firewall does. No gateway forwards network traffic. Gateways are not routers. While it's oriented inwards, it replicates the antivirus server. It emulates the antivirus server to the plant systems. It actively goes out and fetches the antivirus signatures, checks the crypto on them, sends them through the one-way hardware, and stands them up inside the industrial network, sends it off, inserts them into the antivirus server there, and does the same thing, emulates the enterprise resource planning system, goes out and actively fetches the batch orders, again, checks their authenticity, sends them through. So, here's discipline for you. We do not just open another TCP port or 3 and forward whatever packets match the rule on that port. We pull exactly the information we need. We check its authenticity. We send it to exactly where we know it needs to go. There's no network packets coming through here containing who knows what kind of fuzzing or overflow attacks. We don't let network traffic in. So here's a way to do disciplined, scheduled updates. And again, what we've done in sort of the perspective of Psychot is we've modeled the entire control system as the control critical network. We've deployed unidirectional gateway technology at the boundary of that network, protecting the control critical network from external networks like the enterprise and network and the internet. Here is something else. This is an element of enterprise security programs that is fast moving into industrial programs. And it's security monitoring. There's way too many benefits to central monitoring of operations networks to not do it. More and more, we see more and more sites deploying monitoring of their industrial networks. The problem is that every path through a firewall that permits monitoring also permits attacks. And worse, every OT intrusion detection sensor, OT IDS sensor, and you hear so many vendors talking about these sensors nowadays. There's been so much venture money come into this because enterprise security teams are buying this technology in the last 2 years in ways they just never did before. Deploying these intrusion detection sensors, well, you need to connect the sensor on the one hand to the enterprise network so that the SOC can manage the sensor. You got to adjust these things on a regular basis. And you've got to connect the other end of the sensor into the industrial network, into the switches, so that you can monitor the network traffic on those switches. This is a problem. Putting these sensors on the IT network is the right place to put it, but this connection back to the mirror ports is a path back into the industrial network. The sensor is in effect a dual homed host, and we banned these things a decade ago in the industrial space. Now the switch vendors are going to tell you their mirror ports are unidirectional, if they tell you anything. Well, maybe they don't tell you. The documentation is notoriously inaccurate. I've seen switch vendor documentation contradict itself in the same paragraph. In one sentence, it says it's unidirectional, nothing gets back in, and 3 sentences later, I kid you not, it says, oh, but broadcasts can come back in. Why? Because a lot of these sensors can actually be used as intrusion prevention systems as well. You need to be able to send stuff back into the mirror port to interrupt attacks in progress. Only, we don't want to do that. We don't want anything leaking back into our industrial network. We do not want these sensors to become, steal the password for the sensor, and now you can pivot an attack into the industrial network. So we simply can't trust the software switches to be unidirectional. And so what we see people doing is deploying, again, a unidirectional gateway between the mirror ports and the sensor. The gateway emulates the mirror ports to the sensor. This has become a very popular design. In fact, it's so popular, Waterfall released new hardware less than 6 months ago specifically for this use case, a unidirectional gateway that is optimized for emulating switch mirror ports to intrusion detection sensors. And we've partnered with all of the major sensor, OT IDS sensor manufacturers, so that if you have an important industrial site, if you've decided you are going to use the Psychot methodology, you've decided you want physical protection, not just whatever software might or might not be in the switch, you throw a unidirectional gateway in here, and now it's safe to monitor the intrusion detection system. So that's most of what I had for you. At Waterfall, we are the OT security company. We've been around for 13 years now. We've got over 1,000 sites worldwide. We're deployed in basically every critical infrastructure and lots of non-critical infrastructures, manufacturing sites, factories. We have operations all over the world. This is an idea whose time has come. We're growing rapidly. More and more people are embracing this approach to cybersecurity because the threat environment continues to get worse. So before I wrap up, I wanted to make you aware of another information resource. I'm going to put the URL up for the book in a moment. But we also have Waterfall is the sponsor of the Industrial Security Podcast, if you're interested. Again, Waterfall sponsors this as a public service. I'm one of the co-hosts. My marching orders are don't talk about Waterfall. This is not a podcast about Waterfall. It's a podcast about industrial security. We have a different guest every episode. The guests can be vendors, they might be government agencies, they might be owners and operators, but they're always talking about their view of the elephant, their perspective on industrial security. And I can say that it's been running for 1.5 years. I've learned a lot from these guests, and I hope that that you folks can as well. Go to your favorite podcast app, and you can search for industrial security and subscribe. Or if you're new to podcasts, go to the website waterfall-security.com/podcasts, and you can you can see the episodes. You can pick and choose, and there's instructions there on how to set up your cell phone to subscribe if you want. So, here's the summary. Attack capabilities only increase over time. Attack tools only become more capable. They're like any other piece of software. All of us are responding to this worsening threat environment by increasing the strength of our security postures. The entire curve, the bell curve of security posture strength in every industry is shifting to the right. It's shifting in the direction of those sites who today practice secure operations. So the bell curve is moving. What this means is that what these sites do today is all of our future. And what they do when they apply the Psychot methodology systematically, effectively what they do is they raise the bar to the point where there aren't online risks anymore. They raise the bar to the point where the only way to bring about compromise of the site is a physical attack. And they've deployed physical protection from those attacks. They've engaged with their governments to help them with their physical protections. They've raised the bar to the point where a hacker, sipping coffee on another continent is not a threat to them anymore. That class of attack has been wiped out. There are still residual risks, but those are the residual risks are offline physical risks that are much more manageable than the online, attacking across the internet risk. How do they do it? To review in a nutshell, they inventory information flows and then they control those flows. They discipline those flows. What they do is they deploy physical attack, there's physical protection from attack information, and they deploy the most specific, the most secure physical protections for every kind of information flow that does still have to come back into the industrial site from time to time. So again, if you'd like more information on this methodology, Waterfall still has an inventory of the books. Go to the URL, request a free copy. I think, as I said, we can ship. The only place I think we might have trouble shipping in Europe is Switzerland, but I'm not sure. We'll do our best to get a copy out to you. That's what I had for you. Mike, have you got any questions back on the question queue? Yeah, and if people have questions, answer them in the box there.
Yes, we do have a few questions. Thank you for this presentation again, Andrew. And if anybody has any questions, please do enter them into the questions box. We will remain muted across the lines, so the questions interface is your means to ask a question of Andrew. To start with, I'm going to combine a few of our questions into one. I'll take certain liberties with the phrasing. The questions seem to indicate that firewalls, firewall administrators can configure their systems for outbound access only. And there's a comment, a question, how is this different from a unidirectional security gateway?
That's a good question. This is a common confusion. People who have spent the last 20 years working with firewalls, they look at the gateways and they say, well, the gateway looks like a one-way firewall. This is a mistaken impression. The gateway is not a firewall. So, how does the gateway differ from an outbound only firewall? Well, first off, there's no such thing as an outbound only firewall. All firewalls allow packets to move in two directions. When people talk about outbound only firewalls, they're talking about firewalls that are configured to allow TCP connections to be initiated from the inside, from the protected network to the outside, but do not allow connections to come back in the other way. Once the connection's established, though, on that connection, you can send information both ways. So, for example, it's possible to configure a firewall to say allow connections from a web browser on the industrial network out to a documentation server with all of my procedures and policies on the enterprise network and pull PDF files back in. And of course, if the enterprise server is compromised now, if the PDF files are polluted with malware, now I'm pulling attacks through the one-way outbound firewall. I'm pulling it back into the industrial network, aren't I? So the outbound only firewall is sort of a misnomer. Even if those encryptions those connections are encrypted. A lot of people, they talk about secure communications when really they mean encrypted communications. They assume secure communications will prevent all attacks. Well, if I'm pulling a compromised PDF through an encrypted connection into my control network and then launching the PDF, I just pulled an attack through the encrypted connection, didn't I? In what way did secure communications save me from this? It doesn't. So really the question is not, is this an outbound only firewall? The question is not, are my communications secure? The real question is, can any attack information, any information at all, because all information can be an attack, can any information at all leak back into my protected network? This is the difference. The gateways, they're one way, physically one way, whereas firewalls are not. And B, firewalls are routers. They forward network traffic from one network to another. Gateways never do that. The gateways are endpoints of communications for each of their networks. The CPUs on either side of the gateway are endpoints of communications, and they interact with servers and clients on each of their networks. None of those packets make any sense to forward. So, for instance, if I query a historian database server and I get a response back, does it make sense to take that query packet and send it to the enterprise network? No. The queries are useful on the industrial network. We don't need to query the enterprise network. We need to insert data into the enterprise database. It's a completely different conversation with completely different packets. None of the packets make any sense to forward. The gateways are not routers. They replicate servers. So that was a long answer. I hope that made sense, Mike.
Thank you, Andrew. We have another question from a couple of people. Given that there are travel restrictions and other in-person restrictions in this time of our global pandemic with COVID-19, how are these secure sites, these most secure sites, doing remote access?
That's a good question. A lot of people, when they look at unidirectional technology, they assume that it rules out remote access, and that's not true. I did if you're curious, send me email. You've got my email there. I can send you a pointer to it. I did a session with, who was it? Security Week recently, a webinar. The recording's available on unidirectional remote access. There's 4 or 5 ways that people do remote access routinely, but each of them is different. Each of them is specific to a specific need. So, let me give you just one example. But like I said, if you want more examples, they're in the black book, and send me email. I can send you that recording, the Security Week recording. But the concrete example is something called remote screen view. This is just one of many ways to do remote access. It's the most secure way to do remote access. Classic example is I have power plant with a steam turbine. The vendor, GE, Siemens, ABB, whoever, the vendor is going to give me a warranty on the turbine only if they can monitor the turbine 24/7. How do we do that? Well, we can replicate the turbine historian or OPC server out. Oh, okay, so the vendor can interact with the copy. The vendor systems are expert systems. They have access to their data. It's all good. Okay, but the vendor also, every once in a while, needs to call in and adjust the turbine. Turbines are rotating equipment. The enemy of all rotating equipment is wear. The symptom of wear is vibration. When they find a vibration anomaly that is increasing and they're predicting that it's going to end up in a catastrophic failure a month down the road, they need to call in and adjust these infinitely adjustable devices. And so how do they do it? They call up the site and they say, you've got a problem on generating unit number 3. Can I have an hour at 3 o'clock on Thursday to adjust it? Yes, you're booked. 3 o'clock Thursday comes, an engineer on the inside network, on the industrial network, sits down physically in front of the turbine management workstation, calls up the vendor, says, are you ready for this? Yep, I'm ready for this. Okay, I'm turning on remote screen view, and they press a button on the workstation enabling remote screen view. And the software starts taking pictures of the screen, much like remote desktop, sends the pictures to the gateway out through the one-way hardware and stands up the pictures on a web server on the outside, and the vendor logs into the web server. What they see on the web server with a standard browser is a video feed of the workstation screen. And now they're on the phone. Now, they can see a video feed. It feels like remote desktop, but they can move their mouse all they like. Nothing is getting back through the gateway, thank you. If they want that mouse moving, they've got to give advice to the engineer. So they say, okay, let's bring up the vibration diagnostics. And they can see the mouse moving, and they can say, no, that's system diagnostics. 2 further down, there you go, that's vibration diagnostics. And they can work with the engineer to make the change. But understand, generally, the vendor's personnel are not part of the site's security program. The vendor personnel have not been through the site's background checks, the criminal background checks. They've not been through the site's safety awareness program, the security awareness program. They're outsiders. And so it's not, the engineer on the inside is not a mouse monkey. The engineer is responsible for the correct operation of the turbine. That engineer moves, she's going to move the mouse only if she understands the advice the vendor is giving her, and she agrees that this is the correct advice to apply to this device at this time. The vendor, sees the process as supervising site personnel to make sure that a complex correction is carried out according to the vendor's policies and procedures. The engineer sees it differently. Whose turbine is this? It's not the vendor's turbine, it's our turbine, thank you. And we want to know what the vendor has done to our equipment. And so she's going to move the mouse only when she understands what's going on, and she's supervising the vendor. The site sees the process as supervising the vendor. Each of them think they're supervising the other. Both of them cooperate to get a remote correction done. And remote screen view meets both sets of needs. When the session is done, the engineer turns off remote screen view and it's all over. Nothing, the screens aren't going out anymore, and nothing got back ever. So how is this disciplined control? What's filtering the control instructions? It's the engineer's brain. Advice words are coming into her ears through the cell phone. She is filtering these words to make sure that they're safe to apply to the plant, and she is applying that advice to the plant. This is another kind of disciplined control. Filtering incoming control through a human brain is the best kind of discipline 9 times out of 10. So we're coming up on the end. Do we have more questions, or
well, with the time limits as they are, before I give you the opportunity for the final word of today's webinar, a few logistics for our attendees. Once again, all webinar registrants will receive a follow-up email, which will include information on how to access a recorded version of this webinar, as well as some information for registration for upcoming webinars. For those who submitted questions that we did not answer live online, we will reach out to you via email to ensure that you do get answers to your questions. And of course, we want to thank you for spending your time with us this afternoon. It is appreciated. And now I will give the final word to Mr. Andrew Ginter.
I just wanted to say thank you to everyone and remind you to check out the Industrial Security Podcast if you're interested in lots of different perspectives of industrial security. And to go to the Waterfall website, request a free copy of the Black Book if you're interested in that. If your own company policies prevent receiving free books like this, and you're interested, it's available on Amazon as well in both hardcover, softcover, and Kindle formats. So thank you again, and here's my email. If you have other questions, don't hesitate to get in touch with me. I learn as much from interactions with you folks as you might learn from me. So please do reach out. Thank you all. Oh, Mike, you've gone on mute.
Apologize. Thank you again.
Okay.